Hello everyone. Here we're going to be talking about the dynamics of the Nash equilibrium. So, in terms of getting to the Nash equilibrium and the market dynamics of how that operates, when we think about the equation for the Nash equilibrium now as number of hours of fishing, which we'll look at in a second, we say that what the effect of a change in alpha or beta would be, we use what is called comparative statics. Now with comparative statics, what happens is that it's a pardon me, it's a method which analyzes the process of change by comparing the status quo Nash equilibrium with an equilibrium after some change in the underlying data of the problem. So if the size of the effect of the externality changes when beta changes or when there's a change in the initial level of productivity, such as with alpha, you can see how a change in alpha or beta would change the Nash equilibrium of the interaction between Abdul and Bridget. That would be a comparative static analysis. We compare one Nash equilibrium when certain parameters hold with a different Nash equilibrium when different parameters hold. And we see the number of hours of time they would spend fishing in each of those circumstances. That is comparative, we're comparing the two. Statics, we're comparing two static outcomes, both Nash equilibria, with each other. Comparative statics. Okay, now that doesn't tell us how players get to the equilibrium or what their decision-making process looks like when they're doing that. So to think about that and think about things where it's not just about comparing outcomes, we're going to try and look at the underlying dynamics of the problem. So let's remind ourselves of the Nash equilibrium of the interaction, how we visualize it. So we see there the equation for the Nash equilibrium outcome is HAN equals HBN equals alpha over 1 plus 3 beta. Now that's when there are two fishermen, Abdul and Bridget. They're each going to fish that number of hours. So what we can see here is with the given parameters, what are we going to end up at? We're going to end up at H superscript AN being equal to 12, and the same thing for Bridget. They're both going to fish the equal number of hours, and both of them are going to fish 12 hours. Okay, so when beta equals 0.5 and alpha equals 30, these are the 12 hours that we're getting. So for those given parameters, that's what we end up with. So notice that when Bridget doesn't fish, Bridget doesn't fish when Abdul fishes for 15 hours, and Abdul doesn't fish when Bridget fishes 15 hours. So we can see that through these intersections, these intercepts between the best response functions with the x and y axes respectively. So when we have those intercepts, we can see what the one would do when the other one fishes 15 hours. And so if Abdul fishes 15 hours, Bridget doesn't fish. When Bridget fishes 15 hours, Abdul doesn't fish. So those are the points that we think about with their best response functions. Now, where their best response functions intersect, that is the Nash equilibrium. That is a mutual best response that occurs at point little n over here. At point little n, that is the Nash equilibrium. Now, that told us what the Nash equilibrium was, but it doesn't tell us what the dynamics are of reaching the Nash equilibrium when they're out of Nash equilibrium. So to do that, we're going to think about the marginal benefit and marginal cost curves. So as a reminder, our marginal cost curve for each of them is just simply equal to their hours of fishing, HA for Abdul and HB for Bridget. And then we also have a downward sloping marginal benefit curve where the marginal benefits of fishing an extra hour are decreasing as you fish more hours. So that's what we have for here. We've got a set decreasing marginal benefit curve for when Bridget fishes 12 hours. So we can say we've set HB equal to 12, and we then have this downward sloping marginal benefit curve for Abdul. We have the still consistently upward sloping marginal cost curve. And then when Bridget is fishing 12 hours, for Abdul, his marginal benefits equal his marginal costs at point N, and we can say that that is going to be his best response. So when we think about that, this graph is helping us determine what HA should be, because if for some reason Abdul started away from fishing 12 hours, what is the calculation that he would be going through? So if he started at fishing 6 hours, so we were thinking about this point over here, we'd have 2 points on his marginal benefit and marginal cost curves. And we could see that if we compare, I'm just going to label them points G and H here, if we compare points G and H, at point G, we've got a specific level for the marginal benefits at point G, and we've got the same corresponding thing for the marginal costs at point H. We can see that his marginal benefits are greater than his marginal costs. Because he can identify that his marginal benefits are greater than his marginal costs, at 6 hours, he's going to increase the number of hours that he spends fishing until such a point as his marginal benefits equal his marginal costs. Now, let's look at two different points. I'm going to call those points J and K. And we're also going to think about them applying at 18 hours. What we can see there is that the marginal benefit curve, that point, is lower than the marginal cost curve at point J. And so when we're thinking about that, what is Abdul going to do? Well, his marginal costs are greater than his marginal benefits. So he, at that point, if he's fishing too many hours, what should he do? He should reduce the number of hours that he spends fishing. And so his x-axis variable should decrease. And what we can see is that in both of these circumstances, the arrows are indicating either increasing the number of hours, increasing the hours you spend fishing as you are trying to, as marginal benefits are greater than marginal costs. So increase the number of hours you spend fishing as marginal benefits are greater than marginal costs, or decrease the number of hours you spend fishing as marginal costs are greater than marginal benefits. Now, we can see that the direction that those two are pointing in are at the Nash equilibrium number of hours. Okay, so this is what's happening for Abdul. He's always thinking about his marginal benefits and marginal costs. Bridget is doing the same thing. She is thinking about her marginal costs and marginal benefits. So what we can do is we can capture these same ideas in the figure with our best response functions. So what we can do here is we can think about the two best response functions for Abdul and for Bridget. So what we see here is that the horizontal arrows show the direction Abdul will move if he is initially at the base of the arrow. Okay, so we've got the base of some arrow, and then the arrow direction indicates the direction in which Abdul will move. So his arrows are green, consistent with the color of his best response function. His arrows are always horizontal. Okay, they're always pointing towards his best response function depending on the marginal benefits and marginal costs. So we can see here with the 4 different bases of the arrows, we can see different potential calculations that he would make. At the top, over here, where marginal benefits are less than marginal costs, what is he going to do? He's going to reduce his number of hours. So he's going to reduce his number of hours there. Similarly, down here, where the marginal benefits are less than the marginal costs, below Bridget's best response function, he would similarly reduce the number of hours he spends fishing. At other points, though, he would increase his number of hours that he spends fishing. At those points, his marginal benefits are greater than his marginal costs. We can see that for both of these cases. So when he is to the right of his best response function, he would do better by reducing his number of hours. When he is to the left, he will do better by increasing his hours. Now, Bridget, what do we see there? Her hours are along the vertical axis. We have the Nash equilibrium number of hours being 12. And so we can see that for her, we've got downward arrows when her marginal benefits are less than her marginal costs, and she should therefore reduce her number of hours spent fishing. We also see that there are cases where she should increase her number of hours spent fishing when the marginal benefits of an extra hour of fishing exceed the marginal cost of it. And for each of them, these arrows indicating the dynamics suggest to us either the increasing or decreasing of hours spent fishing that will take them towards the Nash equilibrium. So, the inequalities involving the marginal benefits and marginal costs are the reasons for the movements shown in these arrows. These dynamics of the choices that they will make are then going to affect the choices that the other person would make. So obviously, if we started at a point down here where in this kind of bottom right corner, we would see that Abdul is fishing a lot and Bridget isn't fishing that much. So because Abdul is fishing a lot, he should reduce his number of hours. And because Bridget isn't fishing that much, she should increase her number of hours. Now with that, what do we see and what do we think? Well, we think that with Bridget increasing her hours, that's going to change the marginal cost and benefit calculation for Abdul. Similarly, if Abdul reduces his fishing, that's going to change the marginal benefit and marginal cost calculation for Bridget. But the arrows are showing us general ideas of these calculations for each of them in the different areas of the figure. And so we're seeing how marginal benefits and marginal cost, that marginal analysis, is leading us to some dynamics that tell us how we will get to and end up at the Nash equilibrium from different points of our figure.